to have part two, and we are recording. Okay, great.
Oh, good morning. Thanks for coming back for a continuation of what my informal, somewhat informal introductory lectures. As we get deeper into the school, introductory appears to be more and more informal, but I hope that it will still benefit you from giving another perspective, an additional perspective. Well, that's good. Actually, so I heard the air conditioning is on now. So
Air conditioning.
oh, when I got up to my office yesterday afternoon, it was like 85 Fahrenheit. So
We have 79 today.
There were a couple of things I want to get started with to sort of address a couple of very good questions, very simple, very good questions that came up in the course or at the end of the last lecture. So I don't know if the people who asked the questions are here, but I'll use the blackboard for this. Okay, so this is really, really simple. Just to remind ourselves of something. We had one formula that's up on the slides, a few slides before, and that was of the general form that said the time that a virtual state lives is, I'll say, goes like or is equal to h bar divided by the energy of the initial state minus the energy of the virtual state. And it's interesting because this is the case for all the virtual states, but there's only one initial state when you're calculating an amplitude. And so this is the way we calculate the amplitudes. And basically this is Feynman diagrams. Propagators are just combinations of these E initial minus E virtual, different basically by partial fractions. So somebody asked, well, how long is it? Okay. How do you tell how long is it? Well, the way to tell is there's this formula, which so that's the question is how long? Well, as a function of this energy deficit, E virtual, E initial minus E virtual, and you get this from the relationship, which I am right to an order of magnitude anyway, which says something like 200 MeV times 1 Fermi is equal to 1. And so this is in units. People say, well, this really is in what's called natural units, where H bar and C, or you could, for this, you could just say the product is 1, but you can make them individually 1. And you say, well, why is this like part C equal 1? Well, this has the energy, the units of energy. H bar has units of action. Action is energy times time. Multiply action times a velocity, energy times time times distance over time. Time cancels, you end up with energy times time. So the units of H bar C are the units of this thing. And if you set H bar C equal to 1, well, this is an equation, okay, divided by H bar C. So, and then, so here you have a distance, and you say, well, how long? Well, it would be, since C equals 1, it's how far light would go in 1 Fermi. That's the time associated with this. So suppose we had an energy deficit of 1 electron volt. How long would that be? Well, we write this in a different way. Or we'll say, how far would that go at the speed of light? 1 Fermi is equal to 1 divided by 200 MeV. And if we wanted to know how far light would go while the virtual state lived with an energy deficit of 1 MeV, what should we multiply this by? This is 1/200 MeV, which is 2 times 10 to the M11, right? No, 6, 7, 8 EV. So if we want to get a distance for 1/1 MeV, we multiply this by 200 MeV, or 2 times 10 to the 8th. Then we'll be left with 1 over an EV. So you say, oh, 10 to the 8th Fermi, how big is that? It's about the size of the word begins with A, atom. It's about the size of an atom. So that's the virtual states of an atom are living about the size of an atom if the virtual state is like some atomic excitation of an EV. So it sort of makes sense. On the other hand, 1/200 MeV, which was the kind of virtual state that you get by an energy deficit by emitting a pion, a couple of pions or something like that. There, the time scales are the distance, the time it takes for light to cross 1 Fermi. But 1 Fermi is, roughly speaking, the size of a nucleon. So the virtual states that are the natural lowest order virtual states for atoms live about the size of the atoms. And that's how the atom somehow communicates with itself and knows about these things. Similarly for the nucleons. So this is just to to put some kind of number type thing, because after all, this is like physics. Okay, now very much related to this is a question that was brought up with this mysterious figure of this sort, where what we wanted to do was to define our, you were charging it. To define our, thank you, define our coupling by the likelihood for, say, a fermion to enter some sphere of radius r in space-time and then come out as a fermion plus a gluon, or a fermion plus photon, okay, something like that. And so my claim was that, in fact, you can calculate the derivative with respect to this radius. And that will tell you not the value of that coupling, but how that coupling changes with the distance. Well, somebody didn't agree. Okay, so anyway, I'd like to sort of give you an idea of how this formula here comes and gives us an idea without doing any major calculation, although we do have to use some common knowledge of what the derivative of this quantity with respect to R is like. Okay, so here, now that we have some scales, we've related these quantities to actual scales that we're familiar with. Let's look at this picture again. Not terrible. Okay. So this is a radius r. Say a fermion comes in, and then somewhere in here. Oh, this is really, yeah. I mean, it's going to emit. So this is our lowest order. If this were the only thing that happened, we could say, well, this likelihood is just the charge here is G. Once we normalize for the volume. But now we say, oh, keep this picture. Okay, it's coming straight in here. Whoops. And it's coming out here like this. So this is sort of P, and this is P prime, which is equal to P minus K, and this is K, right? But we could also have this. Now, I drew it like it's a gluon with coils, but actually what I'm thinking of is a photon here to make it simpler. And so we're looking at this particular kind of process. Okay. Now, let's look at it from the point of view of this. So I wanted to claim that the amplitude for this to happen inside this volume is given by just applying this rule here. At least this rule will give us a way of understanding this. So what happens is P comes in, it enters a virtual state in which it gives off a vector particle, and that gives us a new state, which we'll call A. Then, while that vector particle is sharing some of the momentum P, that's when K is emitted. Then we have minus K minus this momentum, and that's a new virtual state, which we'll call B. And now the issue we have in quantum field theory is that there's this virtual particle whose momentum we can label by Q, okay? And we want to sum over all the virtual states that can occur regardless of what Q is, right? That's what we're looking for, is whatever Q is. We can't leave anything out because that's what Schrodinger told us to do, and Heisenberg and all those names. Okay, so we have no choice. So let's see what happens, okay? And of course, terrible things happen because there's so many states Q at very, very large energies that we can't sum them up. So what we're saying is, okay, I'm not trying to get the full answer, but I just want to see how this behaves when I change R, right? So, in fact, I'll make this a logarithmic derivative because I'm about to change it to a derivative with respect to momentum. Okay, I've never actually done this before in the board, so this is this hopefully it'll work out. Okay, so so we want d by the r of this, and so what we're saying is, well, okay, what happens when I change r? Well, most of this integral here over, okay, let me say what we have here. So this is equal to r d by dr. So I haven't done any derivative. Well, the sum over states is given, it's just the invariant sum over states, which is the integral d4q times delta of, in this Q, to get the energy of this, we have to put Q on shell because these are real states. Here we started with the initial state, which is just this particle of momentum P, but here we have a state A, which has the energy of P minus Q over here, and Q over here. Right? And then when we come over here, this is P prime minus Q, and Q, and then it comes back as Q. So what we'll say is, okay, well, really, what is this? Well, this is the integral of the states is given by the integral dq q. Next, right? There's no off-shelfness here. Right? When you play this game, you only deal with real live states. Well, to the extent you could call it real. But anyway, there it is. And then you want to understand what other normalization we have, 2 Q, and but you also have factors here of, so the omega Q for the vector is equal to the absolute value of Q, and for there are 2 other particles, omega P minus Q, that its energy is the square root of P vector minus Q vector squared plus m squared. And similarly for, whoops, p prime minus q, it's the same thing. So we have 2 omega p minus q, 2 omega p prime minus q. This is the sum over states. This is the measure for the sum over states. Okay. So now, what do we want to multiply this by? Well, according to this, just to sort of show that this is related to something. I hope I can find this. Oh yeah, here we go. Right. So you see this amplitude to go through some process is given by e squared, and then there's this delta TV over h. So that's a product of e's. So we need to do the two e's, the two denominators, right? And then we have to wave our hands a little bit to talk about factors of particle energy, which has to do with the spins of the particles. So with this in mind, these set of rules in mind, we are summing over states. So here's how we have the correct normalization, I think, for the sum over states. I'm leaving out 2 pi's, but you can put 1 over 2 pi cubed if you want to. And then you have 1 divided by E minus EA. So E initial minus EA, 1 divided by E minus EB times, I'll call it spin momentum factors. And if you really think about this a little bit, these are literally Dirac spinners and polarization vectors. So, but in particular, they're the Dirac spinners for these two virtual particles. They're virtual particles, but we don't treat them like they're off shell. They're not off shell in this sum, they're on shell. So these are, as Q gets large, which is what we're going to be interested in, this very, very large Q, much larger than P. And this momentum are also large, and they're recoiling against this momentum because we're interested in how are we going to organize the effect of these very, very large momentum. Okay. So now this is it. I mean, this is that formula. And here, so for this process here. Okay. However, not quite all states are available to us. The reason is it's not so much, you see, we can't, when Q, so now we have to ask, when Q gets really, really large, right, the de Broglie wavelength is really, really small, and we can easily fit a very, very high momentum particle inside this sphere of radius r. The larger the momentum, the smaller it is. So it's just like shrinking down to this little point here. Okay, so no problem there. So everything is going up to infinity. Okay, so here's a big question, exclamation point. This is ultraviolet divergences. This is what it's all about, the counting of states. So it's so exciting that I'll put 2 exclamation points. But I still got 3 exclamation points in store for you, which is the secret of renormalization or theory of field theories, effective field theories, everything. So now let's just see. That's the upper limit. There is no upper limit. Well, what about the lower limit? What happens when Q gets really, really small? So it's small enough so that it becomes almost negligible. What's happening? This vector particle has a de Broglie wavelength, which is getting longer and longer. And when the de Broglie wavelength of Q no longer fits into the volume, there you have a cutoff. You're not getting contributions from those long wavelength particles that are not fitting inside the volume. So here, we can say there's actually a cutoff, and you say, well, what cutoff would that be? This would be 1 over R. For wavelengths longer than R, which means a Q less than 1 over R, we no longer get contribution from those virtual states. Okay, this is this is true hand waving, but it's actually true. This is what we would mean if we could set up such a thought experiment. And you know, thought experiments have a way of coming true in life, like things like the double slit experiment. So, okay, so here we are. So now so what we're really interested in, however, is what happens when, you know, R is kind of small, right? So let's choose R to be big enough so that it's larger than the external energies that we're talking about. It's as large or larger than the external energies. That's okay. So again, we are taking a derivative of a function that we know is ill-defined. In fact, it's infinite. It's not here. No, if you have an upper limit and you make that go to infinity, the whole thing will diverge. But we can ask how do we know it diverges? So for large Q, so when we say large Q, we don't have to worry about on shell or off shell. Large Q means states with large momentum in whatever frame we're doing this calculation in. Okay, so Q gets large, and we'll say it's much greater than omega P or omega K, the external energies, and therefore omega P minus K also. So then for omega P, okay, so let's look at the way these different factors behave. This behaves like the order of Q cubed. Right, that's kind of simple, right? Now here we have, in the counting of states, 3 factors of 1 over 2 omegas, but all these omegas are increasing with Q. The P and the P prime, those don't matter much anymore. So this behaves like the order of Q to the minus 3. Now, what about these guys? Well, the thing is, this is, so EA minus, so E initial minus EA is literally just equal to omega P minus omega A, which is omega P minus Q minus omega Q. Right? I mean, it's just the energy we had, and here's the energy of the on-shell state. And the same thing for B. So how does this behave as Q goes to infinity? Instead of canceling, this omega P depends on the absolute value of P minus Q. So as Q goes to infinity, it just goes to infinity. So this thing behaves like 2 omega Q as Q goes to infinity. Okay. So, yeah. So this goes, as you say, like the order of Q. And the same for B. Same for B. What a relief it's working out. Okay, so these two, these go like Q squared, okay? And then, okay, so here we have spin-dependent momentum factors. What are these? These are just these are essentially the Dirac spinors. And when you look it up, these are the Dirac spinors for these internal mirrors. Now, for Feynman diagram familiarity, you'd say, oh, well, this here has P slash minus Q slash. For the propagator over P minus Q, quantity squared minus M squared in covariant perturbation theory. So basically, that K slash is the Q slash here. It's the big thing, and that's what we're getting here. And so there's one from each propagator to cheat, and we'll just call it this, the order of Q squared. So what this tells us is this integral is diverging and it's diverging logarithmically. Okay, so this is the UV divergence, is the behavior of the integrand is going like actually 1 over q cubed altogether, but the volume is increasing like 1 over q cubed. You say, what volume? What volume? It's the counting of states. Okay, this is what this is all about. So, okay, having observed that, we say, gosh, it really is divergent, right? So it's logarithmically divergent. Although it's logarithmically divergent, now here comes the part which was the realization people made that led to this big idea called renormalization. You can't calculate from first principles this integral because it doesn't exist. It's ill-defined. But you can calculate the dependence of this integral on its lower limit. We're not trying to get the integral on r d by dr. By concentrating on r d by dr, we're just asking, what does the integral look like at its lower limit? On the volume of states where the absolute value q is equal to 1 over r. It's that finite volume sphere or shell in kind of Maxwell space for when you do, statistical mechanics that actually determines the derivative with respect to r, whatever r. And so, okay, so it's logarithmically divergent, but r d by dr is finite. And that's what enables us to calculate. So if we define this to be the effective coupling or decoupling in the theory at the scale r, or a momentum scale 1 over r, right, then the derivative of that coupling is finite and can be calculated. And that's how we calculate the beta function. Okay, this is, so I never gave this a name, so let's give this a name at the very beginning. We'll call this G effective of R. Okay, so R d by dr of G effective. Okay, now I'm going to do something which is not too terrible because you can even do it in your notes. I'm going to call it G effective of 1 over R. Okay, for the reason that these effective couplings are usually, or running couplings, are given as in terms of momentum rather than distances. But the distance picture is just the same as momentum because the only thing that matters is what's happening just at the edge, okay, where the wavelengths are finite. Alrighty. So this is, I'll just say it was finite and can be calculated. Calculable. Sorry, don't worry, you're not going to calculate it. But so that I hope ties together for you this idea that it's a description of the theory in terms of sets of states that enables us to actually define what we mean by a coupling that changes with scales in a theory that's full of this flickering vacuum where virtual states are coming into existence and going out of existence. Okay, it depends on what scale we're probing the theory. And of course, we want to know what kind of experiments do we do where we can isolate this G effective of K, right? And that's the job of perturbative QCD. And we'll come to that as we go along. Well, this was supposed to last for 5 minutes, but that's okay. I don't have that many slides. So are there any questions here? I mean, this was like supposed to try to be clear, but of course it was a bit of stream of consciousness.
Could you explain more about why that one is finite? probably I just missed.
Oh,
Why that RDR
this
is,
is a perfect question, right? Because it should be clear. Because when we take d by dr, we set the r equal to finite. So this means this r equal r, oops, equals the absolute value of q minimum. So we take d by dr, we set ourselves at the minimum value of q, and now the integral is finite, because the problem with the integral was from infinity. We're not sensitive to infinity at all, and it's only the bottom part that's going up and down. Now, it's interesting because there's a kind of terminological issue here. This looks like an infrared cutoff because it's at the lower end of the sum over integrals. But what, of course, we're interested in physics is what happens for smaller q. And there, once we have this effective coupling, we can calculate everything, where this 1 over r will appear as if it will appear as the renormalization scale, which at lowest order we can think of as a cutoff. So everything up to here, we're essentially saying, okay, this is infinite in the theory we currently have, but we're going to call this the effective. We're going to call it that. And now, once we do that, we can calculate everything at the lower scales, compare it to experiment, and extract the value of this thing. So we get that from experiment, but it's changed with R. The theory makes a prediction. How does the theory make a prediction? Because the theory tells us what initial states, tells us what spins. So everything is determined, and then we can check the theory by doing experiments at different scales, 1 over R. So this is really like the perfect question. Why is it finite? It's finite because we had an overall logarithmic divergence, and we're sitting ourselves at some point in that logarithmic scale. And it's just amazing. And that's always the case in perturbative calculations. You can essentially never calculate the absolute value of any quantity. Occasionally you can. The G minus 2 that actually this contributes to, it actually contributes in a finite way. And the reason is because the G minus 2 here, the spin momentum factor for that particular quantity doesn't grow like Q squared. So it's actually finite. So you get alpha over something. And that, then you get to Nobel Prize, unless it's already taken. But it's cool. Okay, so there, in terms of the lowest order coupling, you can actually calculate the absolute value. But most everything else that we do in QED and QCD, in the rest of in the weak interactions, we never calculate the absolute values of functions. We calculate, but we can calculate their momentum dependence. All right, which also is a reason why it's important to have experiments that have a momentum range, because that gives you new ways, intrinsic ways to test your theory. Okay. All right, so here we are. Now we'll just sort of race through the rest of the slides for today. Well, first I have to get, oh gosh, it's nice to have chalk dust on your hands, actually. Okay, so this is, good, I got it right first time. All right, so that's the world in action. I love it. Well, remember, this is our electron in real life, an electron that spends part of its time with friends, okay? Well, what makes QCD different than the electron, which we can say is pretty much, and we're about to use that too. In fact, we're building the whole EIC to use that. The fact that the electron spends part of its time with friends and not so many friends. It has like a closed circle, which starts with a single photon. And it's that single photon friend that runs everything that in some sense we study in this course, in this school. So the quarks are very, very different. However, why the states with 2 extra gluons, so here, states, I said states with 2 extra gluons. By that, I meant states that look like this. Here's our lowest order thing. The R is not a particle. That's the radius of the sphere, just the same thing we were talking about there. So this is a gauge-dependent statement, but let me not dwell on that. Here we have states where the gluon, on the way out, the gluon splits into two gluons and then continues on. Okay, we have something like that in QED too, and that's in fact the real source of the running of the QED coupling. But here, this is one of the contributions. So what you find in QED is that each of these each of these diagrams increases with R. So the bigger R is, the more positive contribution you get from these states with two gluons in it. The two gluons could be here, but actually the two gluons could also emerge directly from the quark coming in and the quark going out. But okay, this again depends on the gauge that we choose. And so here's one with one such self-energy diagram that has this extra state, right? This is really, it's like just one extra state here. This has two. Each of these diagrams increases with R, and for R about equal to 1 Fermi, which we saw from before means 1/200 MeV, all of these contributions are equal. Okay, and so what's happening then, instead of this nice simple example that we just saw a few minutes ago, where the lower limit, the 1/R, is R, gets smaller and smaller, it's well behaved. Here, by going to higher orders in perturbation theory, we see that there's a series, not just one diagram, but a whole series of diagrams that add up eventually to infinity. And so the idea then is that, so this is essentially, this is the flip side of the famous property of QCD of asymptotic freedom. For smaller R, so therefore higher and higher cutoff, we get weaker forces because G sub S will decrease as we go higher and higher. But for larger R, which means taking the lower limit lower and lower, we get stronger forces. And out of this, we observe that QCD is at least consistent from a perturbative point of view with the observation, never mind the concept, of confinement, that there are excitations or that there are degrees of freedom at very short distances, which when you go to longer distances are always confined in bound states. Okay. Of course, it's not something that's proven, and people say, oh, you could win $1 million. Well, $1 million is what it used to be. But then again, it's not bad. It's the fame. It's the fame. So prove it if you can. Okay. So now I'll just take a little bit of an excursion here, and after our discussion of last night, I know a lot of you know more about these kind of calculations than I do, but I think it's worth pointing this out or discussing this in a minute, in the context that we've discussed the perturbative expansion. And then so the idea is what happens when these couplings start to get large? When the couplings get large, then following these individual changes in state that we specified for the way the system, you start with a list and then you change the list by perturbatively, vertex by vertex, this gets out of control because the effective coupling over periods of time long compared to, or of the order of 1 Fermi, will no longer be convergent. So what you do, and was discovered by Wilson and by many of us, a series of great works, is instead of specifying a list of particles, you specify fields or an array of fields at some time t, a lattice of points in one, a lattice of points in space at time t. Now, in the gauge theories, you really have to make this more complicated. You don't talk about lattice points only, you talk about links, you talk about plaquettes, But it's the idea that you work with the fields themselves instead of with their excitations. In a sense, it's like, so like working in coordinate space instead of random space. And then you take any sets of fields. In general, you go through many, many of them, and you work in a statistical fashion, and you evolve that system. So I've just drawn some of the points here. Obviously, I should cover this whole thing with birds, but that takes too long. You evolve for some time, delta t, or in this case, it's little t. But it's over already?
Move it away.
Okay, yeah. This is like the Gong Show. Okay, so we evolve according to what the Schrodinger equation tells us to evolve when we have specified fields instead of particles. Okay, and the Schrodinger equation then says use a path integral. Let me just cut to the chase, which is using the factor relationship of least action or going near least action. Least action is the classical evolution, but you go around that by using the path integral formulas. And then starting with some particles in the initial state, you can calculate the correlations with particles you test for in the final state. And if there were no forces between particles, if this were just a free theory, any correlations you put in here would basically disappear, wander off. But in fact, what you find is correlations in values of the field. So for example, up, up, down, for example, emerge as exponential behavior, decreasing exponential. And here I don't write it down, but we're going to Euclidean space, in other words, an imaginary time. And by looking for correlations that decrease exponentially with different values of m, you observe that there are bound states. And you know this quite well, and for states of various masses m. And we can compute other correlations, and this is what it's all about when you hear people talking about calculating PDFs and TMDs and soft functions and just everything on the lattice. It's all in spirit, at least I think I've captured the spirit here, derived by starting the viewpoint of using the spirit of the Schrodinger equation to tell you how you go from a set of fields to a set of neighboring fields, and doing this for a statistically large amount. This is what lattice QCD or lattice quantum field theory is one way, at least, of looking at it. Okay, and all this means that so now we go back to being extremely informal. This is informal. This is extremely informal. All this means that the states of QCD are really different, right? And that's what I would like you to take away. It's different precisely because of the way that partonic, the degrees of freedom fit into one of these spheres, which we use to derive the color. So it's the counting of the states and the way they combine it at lowest and highest orders. So they're protons, neutrons, and other hadrons. So when you do look for correlations of isolated quarks in this thing, you don't find them. So it really does confine, at least the numerical evidence is overwhelmingly that we've proven confinement empirically. And, maybe it's worth saying, for those who. Okay. So anyway, I mean, there's a couple of things here. You can draw something like this. Like I got tired making this set of dots. And I had straight lines and I chose the dot option, but it was getting like complicated. But anyway, the question here to connect to real life world, you really want the dots to be essentially on top of each other. The distance between the dots is one parameter, usually denoted by A, the lattice spacing, okay, which is in 4 dimensions. So there's a lot of dots. And then there's another parameter, which is the size of the lattice, where you may choose, for example, periodic boundary conditions. Say the dots over here take the same values as the dots over there, make the world into a big cylinder, and then let the radius grow, something like that. But here, so it's in terms of those two basic parameters, the lattice parameter and the size of the lattice, all of which has to do with the computing power and the skill with which you program that computing power, enables you to actually do these calculations. And your confidence in these calculations is always tested against, well, let me change this A by a little bit and see that I get the same answer. That shows I'm becoming insensitive to it. And then you're hoping you're in the right phase for this system because maybe you're in a completely different phase. So it's giving you a theory, but it's not the theory of the world. For that, you need experiment. That's why this is called physics. And, by the way, I mean, choosing the lattice spacing, varying the lattice spacing is very much related to varying this R here. You see, the R introduces a length scale into your problem, and that's what you have here as well. So all these concepts are related in beautiful, profound ways. Okay, finally, all this means that the states of QCD are really different. So our world, of course, is mostly protons, neutrons, and nuclei they can make. So in our pictures, going back to our partonic pictures, they're valence quarks plus all the things that we could have gotten by applying our old rules to say, oh, I start with a list, I get to another list, I get to another list. So I could have a gluon, I could have C quarks. This is where, the Drell-Yan process came in. Before QCD, people said, oh, there are partons that we can see perhaps in deep inelastic scattering. It looks like free parton scattering. And then people said, Drell-Yan in particular, well, that means if this is really quantum mechanics, we should remember what Dirac said and let the vertex, that whatever the strong interactions are, they should be producing pairs of quarks. It doesn't change the quantum numbers. And if there are pairs of quarks, it means there are antiquarks around. So if you collide a proton and another proton, two protons, one of them may have some antiquarks in the particular virtual state that it felt like being in. But if that's the case, that antiquark should annihilate. And when it does, with a quark from the opposite one, the opposite proton, you'll see a muon. Well, it'll create a virtual photon, which will decay into electrons and muons. And muons are easy to see because the muon's heavier, so its virtual states don't get to scatter, as we discussed at the end of the last session. And that's how the really quantum field theory, the quantum field theory nature of the strong interactions was revealed by the Drell-Yan process even before there was real evidence for, full evidence for QCD. Okay, so all this stuff here is equal to the protons. So here we're saying this is the bound state, and we can detect those bound states on the lattice. But then again, if we step back, we can think about it in terms of ID settings and later. Hi, Andre, do you want to? Yeah, okay, so here's some statements about the proton, which we already knew about. So again, other classic states, well, all subject to this rule for changing the list, the sum of particles. So we can have the neutron, two downs and an up quark, and then it also has pairs and plenty of gluons, muons also in this selection of states. And it's really the whole idea of the accelerator is once you realize what the states are, you make a target of them, and then you try to find how they're made out of these microscopic or fundamental degrees of freedom. Okay, good. So yeah, again, this is from just the discussion of the lattice again. But here the kind of, so just remember we had this e to the minus mt, and when you really get serious about it, you can find a lot of m's. Not only can you find the existence of states, you can find their quantum numbers by looking for the right correlations at the beginning of your lattice evolution and the end. What you see at the end depends upon what you see. So you can get states with different parity quantum numbers, negative, positive, exotics. Here they are as mass over GeV. You see here it goes from, here's the nucleon sitting here someplace, and various ones. And so these are the kind of things that are being searched for right now in terms with whatever success they're having at this moment. So, okay, now, what a proton looks like, okay, what we've decided is that it's, yeah, you can get it from the Schrodinger equation by saying, yeah, quarks give off gluons split into pairs, sometimes they come back, it's okay, it's good. We know exactly what's going on. But because of asymptotic freedom at large scales, the size of the proton, because 200 MeV, whatever, it's a mess. It's just like there's so much stuff and it's all going all over the place, bouncing around inside the proton and so forth. So these are the things we'd like to learn about. So, however, we look at it from the electron's point of view. It's always good to look at it from the electron's point of view. I think you can broaden your viewpoint, So the electron, which is approaching at nearly the speed of light, a proton, sees the whole thing Lorentz contracted because, from the electron's point of view in its rest frame, the proton is approaching it at essentially the speed of light. So it sees it Lorentz contracted and time dilated. And so as a result of that, all the momenta, which are spread out in rotationally invariant way when the proton is sitting at rest, all of them have been boosted so that their dominant momentum contribution is pointed towards the electron. It's really kind of cool. I mean, it's just, you can't avoid it. So to a good approximation, an electron, now we go back to the electron and its friends and the quarks and its friends, okay? To a good approximation, an electron arrives at the collision, or in its own rest frame experiences the collision, in a virtual state with a single extra photon. If the electron happens to be in its own bare virtual state with no photons around, generally speaking, sorry about that, okay? But of course, there's net charge in the proton, so you could get a photon. Only, however, let's consider it from the electron's point of view. So here it is in that state. It's just sitting there. The photon's nearby, they're talking, hey, how have you been? A proton appears all at once. It's at the speed of light, so there hasn't been any communication without warning, okay? So, right. Okay, so the way I like to look at it is from the point of view of the electron, the proton is flat, it's frozen, that's time dilation, and it's unexpected. And unexpected is the concept of factorization. Because the proton can't communicate with the electron before it arrives, because it's going essentially at the speed of light. Okay, maybe the last little tiny bit, but those are corrections that you can look at and convince yourself they're small. So only that photon, this one here, interacts directly with quarks in the proton. And then you can ask, how much can you get from that? And that's going to be the subject of the next lecture, is how much you can get. And so not to take anything away, quite a lot, okay? When that photon, remember, that's the photon that was the friend of the electron. And because the electron is QED is weakly interacting, generally speaking, the most likely thing is to have only a single photon. So the proton may remain whole, but change direction because it absorbs the photon, in which case that's elastic scattering. It may produce an excited heavier proton. That's quasi-elastic scattering. It may break up the proton. The photon, that is, may break up the proton. That's inelastic scattering and produce other particles, anticipated or not, in QCD. If it transfers a lot of energy in inelastic scattering, it's called deeply inelastic. By a lot, we mean, generally speaking, at the mass of the proton, above the mass of the proton. And we'll see in this, the remaining lecture next time, basically, what we can learn from each of these. Something of what we can learn. You'll learn much more of what you can learn from Alexi's lecture and from. And by the way, at very high energies, states in which it's not just a photon, but by a short-lived heavy particle like the Z boson. Okay. That's another friend of the electron. The Z boson is a friend of the electron, but because it's so heavy, right, its energy deficit is larger. So that state lives a lot shorter. On the other hand, because the coupling of the electromagnetic coupling is relatively weak, the contribution from Z boson initial states at high enough energy gets to be comparable to that of a single photon before you start to get to many photons and things like that. So that's kind of neat. Okay, so real quick, I'm just going to wrap it up right in like 2 minutes here. This item 4, which is a very much a short item, electron-hadron collisions and the dark world. So electron-proton elastic scattering through the Z exchange is, I like this word, exquisitely sensitive to the parameters of the standard model through parity violation, spin-dependent parity violation. So Jefferson Lab has began already with experiments. We measured this over some momentum scales, and the EIC will give us that extra energy range to say, you know, there's couplings there. This thing we like here about the Weinberg angle. And it's basically some ratio of couplings and things like that. And we've seen that when we have a theory, we want to use reasoning. Reasoning like this tells us that if we have the right theory, we'll be able to predict the values of couplings at one scale in terms of those at another. And that's essentially what you can do with this Z boson exchange or Z boson virtual state of the electron as you go to different momentum transfers and test different length scales. And that's something which is going to be very important. Already also at Jefferson Lab, you have the Muller, now it's funded, I believe, experiment, which will look at electron-electron scattering through a photon and Z boson exchange, but even at levels of precision that are unprecedented. And yeah, just to notice, if there's something else out there, you can make it in deep and elastic scattering in particularly clean ways. And this is something that is of great interest to a lot of people here at Stony Brook and all around the world. The electron might have other friends that we haven't seen directly. A new kind of particle, a dark photon, which would be like a portal to dark matter in many theories, not detectable in previous direct detection experiments. An electron might come around, enter a virtual state, or through scattering, enter a state with a dark photon, which could decay back into pairs. And by looking at the angular distributions of these pairs, in terms of, you could determine with sufficient precision and sufficient data, the mass, in fact, of this new state. So here's the scattered electron. You could tell it from an electron-positron pair by the wide angle the scatter would appear at the small angle between the pair produced by this dark photon. Well, it hasn't been seen yet, but it may be just around the corner, whether at JLab or at an EIC. It can also be a portal to the world of concept of leptoquarks, particles that actually, where you have vertices, where you can produce a pair, which is a quark and a lepton. And that's really neat. There was a flurry of interest in that in the around the turn where we got closer to this century. At Daisy, there were events that looked like they were hinting at the quarks. But pretty quick, this was, I don't know, around the year 2000 or a little bit before and after. But the way it appeared at the time where there were so many other experiments that would have seen evidence that you couldn't think of a theory that that would explain it, and then the data statistically went back to expectation standard. But possibility is still there, and there's talk of leptoquarks in the context of flavor violation in high precision physics, usually involving the B quark. Okay, I think this is a good place to take a break. I have maybe 30 slides for tomorrow. But it's all developing things and touching back on things that will have already been mentioned by Alexa for the most part. And a little bit about how this connects to hadron scattering. Okay, so for today, thanks very much.
Thank you.
Well. Well, okay, you'll know where to find me and I'll be around tonight and unless he asks you a question, I mean, I can't stop him.
You don't ask questions, I ask questions. There's one sign wrong there. Have you found it?
Only one?
You made an odd number of errors instead of an even number.
No. The answer is okay.
Oh, yeah.
You
Okay, I see it.
There you go. Okay, change it. I mean, why don't you? There you go. Perfect.
Perfect.
Okay, they were paying attention, George. I was just making sure that they.
Great, no, wow. I'm
Okay,
really,
okay, they see it. Perfect. They still don't ask questions. Okay. Ask questions while you can, because this evening we are going to ask questions. Evan, go ahead.
I actually have a question, but so the question is about that after you boosted the hadron, you say that it's just like be flat because of the Lorentz transformation. But after you change the frame or you do the Lorentz boost, the lambda QCD doesn't change. So like the size of the hadron, mainly like roughly 1 over lambda QCD or something. So that size should stay the same, right? Instead of
its own rest frame, it stays the same.
um
But in other words, what's happening, I mean, in a sense, you think about, well, what about the guys inside, right? They don't feel squashed at all.
yeah.
But how does, but they appear to be to the electron. I don't want to push this too far, but we do know there is a Lorentz contraction, whether this side. Basically, because of the time dilation, particles which are really nucleon distances away, like a Fermi away, which is where strong interactions become very hard. So their interactions go like on a time scale, which is more or less 1 on lambda QCD, which is also a time scale of this size.
Yes.
They are much closer together in the electron's frame, but all the processes are time dilated. So that it takes longer from the electron's point of view, just that much longer for these guys to communicate with each other at that particular scale. So I think there are compensating effects for that. But the whole question about, I think it is interesting, and it's something that people who work in small x physics really think about a lot in terms of, well, what happens when we're looking at a nucleus? And in the nucleus, you have 8 to the 1/3 distance here, and there are all these nucleons. And now you look at it from an oncoming, you look at it from an oncoming electron, which produces a photon, and then that might produce a quark pair, and the quark pair will pass through this material. And how to think about that material? Should we think about it as something which is denser rather than nuclear density, but nuclear density times 8 to the 1/3 divided by some small number, which is the Lorentz contraction, or multiply times gamma, 1 over the square root of 1 minus v squared over c squared. And so how much should one look at this from the point of view of what's the dynamics of such a system? And I think, it's a subtle business, but people have used this kind of geometric picture, I believe, to help motivate models and evolution equations. We'll hear about some evolution equations later, just in the next talk, but evolution equations for this kind of very, very high energy high density scattering. So you hear about, we think about this at small enough X. We look at gluons whose wavelengths are very small, even in the rest frame, and or scales of 1 lambda. Now they've been squashed into the small region, this pair, which we got from the electron, that's being the photon friend plus photon's friends. Oh, you invited them? Oh, shit, here comes a nucleus, we're in trouble. And all hell breaks loose. But to understand what happens, they'll be using concepts like that. So I'm not answering technically, but saying that this is an important issue. Yes, here's,
I think I missed something. So when we see that coupling, effective coupling, we see that at a certain length scale, right? So how do we determine that finite values are?
oh, what the appropriate reading
Yeah.
stars.
Is there any rule?
That will, well, there's a set of rules. And that's the job of perturbative QCD. And essentially, if we give an example, the example comes from, we were looking at it yesterday. Here, okay. We had this particular process, which is, say, E plus E minus goes to mu plus mu minus. Now, if we sum over all of the final states that could be reached this way, not just mu plus mu minus, but plus all possible photons and pairs and things like that, then the coupling we should use, the scale of the coupling, is in fact the total invariant mass. It does not depend on the details of the final state that you might find here. And in particular, if this is an electromagnetic decay here, and then this becomes, it goes to quarks, the scales of all the couplings here will be the total center of mass energy. That would be the scale that's appropriate to use. And to show that actually requires a little bit of some reasoning that we'll talk about tomorrow. Okay, and for other processes, it becomes, here is particularly simple. And this is, I mean, one of the great examples of asymptotic freedom, because then the strong coupling becomes at high energy electron positron annihilation, very weak, even of itself. And you get precision corrections to this total cross section. Now, when you start to look at the cross section, not total, but actually ask how's the momentum distributed in the final state, then you can define quantities with a normal scale R, which is close to roughly the same scale as the total energy here. And you can do that for certain kinds of cross sections, and those are called jet cross sections in this case. So you probably heard of jets, high energy set. And so the mass of the jet, in some vague sense, it's a bunch of particles moving out more or less in the same direction. Its invariant mass is much less than its energy. The mass of the jet gives a natural scale for jet cross sections. And so that's at least giving us an idea of where we're going. But it's a perfect question, you know. In other words, I said, oh, different scales, you could make predictions. And say, well, where did the scales come from? It's not like we have little balloons that we're sticking the target region. All right.
Excellent. Let's thank George. So we have half an hour break. Let's return 20 to 11.
What else do you want? And then when you're done, just drop them on the back table. Thank you.
Okay.
Oh, yeah.
Oh, yeah.
By the way, the software that he's doing.
Do you have an Intel Mac or an M chip Mac? If it's an M chip Mac, technically, so you need to run Docker